out volume of a right circular cone. Now friends, whenever we talk about volume of any object, regardless of its shape or size, what is important to note is that volume of any object is equal to the amount of space that is occupied by the object. This is how we define the volume of any object. Now sometimes the object may be hollow or empty from inside. We talked about earlier as an example, if you look at a room which is in the shape of a cuboid, inside of the room is empty. So what if the room or any object is empty? Then in that case, what happens is we can, if the object is hollow or empty, then the object can be filled with air or gas or any other liquid. In that case, the volume of the object can also be expressed in terms of how much substance, whether it is a liquid or gas, that we can fill into the object. Because the inside is empty, we can potentially put some air or any other gas or any other kind of liquid into the object. So then the volume of the object can also be expressed in terms of capacity of the object. Capacity is nothing but how much of the substance the object can hold. That is the capacity of an object. So it's important because whenever we talk about volume, also oftentimes the term capacity is referred to mean the same thing. So wanted to make sure that you are aware of this. Now let's go back to right circular cone. Now the two most important dimensions that we absolutely need to know for a right circular cone, they are the radius, which is the radius of the base circle, and second is the height, which is the height of the cone from the base to the very top. What is the height? If we know h and if we know r, we can find out the volume of a right circular cone. Similarly, we can find out the surface area of a right circular cone. So the volume of a right circular cone will be equal to 1 by 3 times pi r square h. I have just mentioned this for completeness sake, that L is a slant height. This length is L, this is h, and this is r. So you can think of this triangle which is formed by the dotted lines and this solid line as a right triangle. And applying Pythagoras theorem, we can say L square, which is the hypotenuse, is equal to h square plus r square. The reason I said that is because sometimes if you know two of the three, if you know L, h or r, two of the three, you can find out the third one. Volume of a sphere and volume of a hemisphere. So now friends, whenever we talk about volume, we have seen often the term capacity used almost synonymous with volume. So what is the volume of an object and the capacity of an object? So volume of any object is really the amount of space that the object occupies. That is what is meant by the volume of any object. So what is capacity? Now capacity of an object is really synonymous with volume of an object. Oftentimes they mean the same thing. So capacity of an object is the volume of substance the object can hold or accommodate. Meaning, if the object, whatever the object which is in the question, if this object is hollow or empty from inside, then we can potentially fill that in with any kind of gas or liquid. So in that case, capacity of the object will be equal to the volume of the substance that the object can hold or accommodate. So this is important to keep this in mind. Now, volume of a sphere, we know that the only important measure which is something that we really need to know for a sphere is the radius r. So if you take a sphere and if you basically cut through the sphere, like if you draw a plane that goes right through the middle of the sphere, through the center of the sphere, then on that plane you will get a circle like this, and the radius of this circle is r. So then the volume of this sphere will be equal to 4 by 3 pi r cube. So 4 divided by 3 times pi r cube. This is the formula for volume of a sphere with radius r. So now, what about a hemisphere? So the hemisphere is nothing but if you take the same plane and cut the sphere into two equal parts, each part is a hemisphere. So this is a hemisphere. We saw the word hemi means half. So hemisphere, you can think of this as half sphere, right? So the volume, so our radius is still r. So the volume of a hemisphere will be equal to, as you can imagine, it will be 4 by 3 pi r cube, which is the volume of the sphere, and we will actually make this half. So half times 4 by 3 pi r cube, which is nothing but, this will cancel, so 2 2s are 4, 2 by 3 pi r cube. This is the volume of a hemisphere. The strategy that we need to follow to solve questions on combination of solid figures. So in the last few episodes, we have been really doing a recap for surface areas and volumes of cuboids, cubes, spheres, cones, cylinders, etc. So now we are going to talk about combination of figures, combination of solid figures. So this episode will focus on strategy in solving combination of solids. So the first step is to try and visualize which simple solid figures such as cuboids, cubes, cylinders, cones, spheres, etc. make up the given complex figure. That means we will be given a shape and say we are asked to find out the total surface area of this given complex shape. So the first step is to try and visualize which simple solid figures make up the given complex figure. The second step is to find out which areas. Second step is to find out which areas have to be added or subtracted to get the required area. So the second step is very important. Once we figure out that the given complex shape is made up of either combination of cuboids and cones or cones and sphere, etc., etc., then the second step is we have to figure out which area should be added or subtracted to get the required area. And finally, the third step is to find the individual areas or areas of these individual simpler figures and then calculate the required area based on step 2, right? So whichever areas we need to add and or subtract. So third step is we need to find out each of the individual areas of these simple solid figures that we have learned from step 1, and using step 2 of which should be added, which should be subtracted, do that calculation to find out the required area. This is going to be our overall strategy in solving these type of questions. So one very important thing that you would want to keep in mind, especially when we are talking about areas and surface areas, is that when calculating area of combination of solid figure, this is important. This is true only when we are focusing on calculating areas, not volumes. When calculating areas of combination of solid figure, we do not always simply add the areas of individual parts that make up the solid. Why? Because some parts of the area, they may disappear when we join the parts. So again, this is actually very, very important to keep in mind. This applies only to area question, combination of solid figures, and if we are dealing with areas, calculating areas of combination of solid figures, then this point is very important. We don't always just add the areas. Why? Because some part actually disappear when we join the shapes together. So the parts that disappear, those areas need to be subtracted. So something to keep in mind as we look into these questions. Now I want to help you visualize. So this is a shape which is given to us. So whenever if you get a question like this, what you should be able to do is visually you should be able to see that this can be broken out like this, and similarly this can be broken out like this. So essentially this shape is same as this shape. That means this shape is made up of a cylinder. So this is our cylinder, and then I have two hemispheres. So even though the complex shape here, and this is the same, so even though we have a complex looking shape, we should be able to break this shape down into one hemisphere plus a right circular cylinder plus another hemisphere. And just to reiterate the point that I was making about the area, is that if you add total area of this plus total area of this plus total area of this, will that be equal to total area of this? Answer is no. Because you have to make sure that this area, which is the area of the circle, and this area of the circle, similarly this area, which is the area of the circle for the cylinder, and this area, these areas need to be subtracted. In other words, if I have to join these three simple solids to get this shape, and if I have to find out total surface area of this solid, it will be really the curved surface area of the cylinder plus the curved surface area of the hemisphere 1 and then curved surface area of hemisphere 2. We have to make sure that we take out these surfaces, because when you add them, these surfaces, they disappear. They are not there anymore. Let's take a look at one more example. So now we have something like this. So you should be immediately able to visualize that this can be thought about as like this. So idea is for you to be able to visually see that you are given one complex shape and you are able to visualize this as combination of a cylinder and a hemisphere. So let's take one final example. Say you have a shape like this. So your eye, your mind should be able to immediately see this shape as a combination of a right circular cone plus a hemisphere. On transformation from one shape to another. Because this is a series on surface areas and volumes, so our focus will be to learn as one thing is transformed from one shape to another, how does it really affect the surface area and the volume of that thing. So let's look into it. So we are going to begin this webisode by talking about how do we make candles. So I know out of the blue it is very surprising, why are we talking about making candles? But believe me on this, we are going to list out some very high level steps of how a candle is made, and we will try and figure it out how it relates to this particular topic. So the first step of making a candle is we start out with liquid wax, and yes, there is something called as liquid wax. So first step is you take some liquid wax. Second step is pour that liquid wax in various molds. Molds are nothing but containers. Third and final step, you let it dry or solidify, and voila, you have a candle. So what is important, friends, is obviously this is an extreme simplification, oversimplification of how a candle is made. But my point is, we start out with liquid wax and we get a solid shape, which is a candle. So what happened is our liquid wax, liquid, got converted into solid. And this is what we are going to focus on, really, how it affects the surface areas and volumes. So let's look into it in a little bit more detail. So say we start out, so I have two containers here, and the liquid which is highlighted in blue is the liquid wax. So imagine this is liquid wax. So I take the same amount. So let's say this amount is V and this amount is V as well. So V is the amount of liquid or the volume of liquid which is in this, which is the liquid wax. Now what I do is I take two different looking containers, and these are my molds, right? So this is my mold A and this is my mold B. They are both of in the shape of a cylinder. This is much more shorter and fatter, or wider, you can say that, and this is much more slender and taller, right? So what I am going to do next is I am going to pour my liquid wax into each of these molds. So I'm going to pour it like this, I'm going to fill it up, I'm going to empty my liquid wax, and I'm done. So now what will happen, friends, is that now in this case in mold A, the liquid wax is filled in this form, and if we let it solidify, we'll get a candle like this. In mold B, if we let it solidify, we are going to get a candle like this. If you look at each of these cases separately, what is very important to note is that the initial liquid that we started off with, the initial volume, let's say it was somewhere over here, and again the same thing over here, right? So this liquid wax that we initially had, that basically was poured into this mold, and that made this candle. So what is the connecting factor in between these two? So the common factor that binds these two is that this liquid wax, which was of volume V, that made this candle. That means because this is a cylinder, so we know that so cylinder has a radius r, and let's say the height of this is, because we have two scenarios, let's call this R1 and this height as H1. So the amount of liquid wax in this will be given by the volume of the cylinder, volume of this cylinder. So volume of this cylinder will be pi R1 square times H. Now this volume, that which tells us how much liquid wax is in there, because capacity of this cylinder is the volume of the liquid wax in there, that this must be equal to the volume here, which was a starting volume of liquid wax. So very important point, friends, which we are making here is that the volume, when a liquid, in this case starting here, got transformed into solid in here, the volume remained the same. So if we started out with volume V, and finally we got a volume pi R1 square times H, because this is in the form of a cylinder, so these two volumes must absolutely be equal. As the state is transformed from liquid to solid, the volume must be the same. Similarly, as you can imagine here, this was a starting volume, and let's say, because we said this was also V, but in this case we got a candle which is very differently looking in terms of shape and size. So let's say this radius, if this radius is R2 and this height is H2, then in this case volume of this cylinder, which gives us how much amount of liquid wax in this, that volume is given by pi R2 square times H2. Now this volume of the solid, it absolutely must be equal to the volume of the liquid wax that actually made this solid. So these two volumes must be equal. So friends, the point that we are looking to drive at is, as we have transformation done from one state to another, right? When one shape is transformed into another shape, new shape, the volume of the old shape remains equal. Volume of the old shape remains equal to the volume of the new shape. This is very, very important. In other words, this point, that volume of the old is going to be equal to volume of the new, this is super duper important. Each asterisk is for very. So it's very, very, very important to keep in mind whenever you have a transformation from one state to another, that the volume of the old shape is always going to be equal to the volume of the new shape. And as we just saw, the reason of that is because you're using the old shape to make the new shape, right? Because you are not adding anything extra. You take the old shape and you use that to make the new shape. So the volume of the old is always going to be equal to volume of the new. Very, very important to keep this in mind, right? So the strategy in solving questions that are based out of this kind of transformation are, we just have to remember that volume of our old shape must be equal to volume of our new shape. So some types of scenarios where you may actually apply this, they will go something like, say you start out with one shape and you melt it, then a new shape is created from it. So that is one type of question that you may come across. The other one could be like, you dig up some ground, and then whatever the soil that you take it out, you then make some shape out of that soil. So again, it is important to understand how much soil did you dig out, what was the volume of that soil, and then that is the soil that you are using to make the new shape.
Thank you for watching our channel. இந்த வீடியோ உங்களுக்கு பிடிச்சிருந்ததுன்னா கமெண்ட் பண்ணுங்க, லைக் பண்ணுங்க, ஷேர் பண்ணுங்க. மறக்காம இந்த சேனலை சப்ஸ்கிரைப் பண்ணிட்டு பக்கத்துல இருக்கக்கூடிய பெல் பட்டன்